Across the arid stretches of southern Israel, where rainfall barely reaches 200 millimeters a year, and summer temperatures regularly climb past 40 degrees Celsius, something remarkable cuts through the landscape. A ribbon of water flows steadily through the Negev desert, not as a natural river, but as one of the most ambitious water engineering projects ever constructed in the Middle East. This is the National Water Carrier, a system that moves over 1.7 billion cubic meters of water annually across more than 130 kilometers of Israeli territory. Built in the early 1960s under conditions that seemed almost impossible, it transformed barren desert into productive farmland and enabled entire cities to exist where survival once seemed unthinkable. The story of how Israel engineered this artificial river through one of the harshest environments on Earth involves technical innovation, political pressure, and a scale of construction that changed the fate of an entire nation. By the late 1950s, Israel faced a water problem that threatened its very existence. The country's population had doubled in just 10 years, reaching nearly 2 million people. But water resources remained concentrated in the north, while most available land for expansion lay in the south. The Sea of Galilee, Israel's largest freshwater lake, held approximately 4 billion cubic meters of water in the northern region. But the Negev desert, which comprised over 60% of the country's total land area, remained almost entirely uninhabited due to severe water scarcity. Agricultural experts estimated that without a solution, food production would plateau within a decade. Urban planners warned that southern development would stall completely. The math was straightforward and unforgiving. Water existed in the north, space and potential existed in the south, and no natural system connected them. The idea of moving water from north to south wasn't new. Engineers had proposed various schemes since the 1940s, but the scale required seemed prohibitive, moving billions of cubic meters annually across varied terrain, through mountains and valleys, while maintaining water quality and managing enormous energy costs presented challenges that had never been solved at this magnitude. International experts who reviewed early proposals often concluded the project was too ambitious, too expensive, and too technically demanding for a young nation with limited resources. Planning for the National Water Carrier began in earnest in 1956, led by Tahal, Israel's water planning agency. The route they designed would start at the Sea of Galilee in the north, located 200 meters below sea level, and carry water southward through a combination of pipes, open canals, tunnels, and reservoirs. The system would need to climb significant elevation changes, cross different geological formations, and deliver water at consistent pressure and quality across the entire distance. Engineers calculated that the main carrier would require pipes up to 2.8 meters in diameter, pumping stations capable of moving massive volumes uphill, and storage reservoirs to balance supply fluctuations. The route divided into several distinct sections, each with unique engineering demands. From the Sea of Galilee, water would first be pumped upward approximately 250 meters to reach the Beit Netefa Valley through a series of massive pumping stations. From there, gravity would carry the water through a combination of open canals and underground pipes toward the Rosh Hayan facility near Tel Aviv. The southern section would then continue through enclosed pipelines all the way to the northern Negev. The entire system would eventually include over 80 miles of pipes, 17 miles of open canals, and numerous tunnels carved through solid rock. Construction began in 1959, mobilizing thousands of workers across multiple sites simultaneously. The scale of earth moving alone was staggering. Excavators removed millions of cubic meters of soil and rock to create open canal sections. In areas where the terrain made surface construction impractical, crews drilled tunnels through mountain ridges, working from both ends to meet in the middle with precise alignment. The Monash Tunnel, one of the longest sections, stretched over 6 kilometers through solid bedrock. The most critical component of the entire system was the pumping infrastructure at the Sea of Galilee. Water had to be lifted from the lake, which sits in a deep basin, up to the highland elevation, where it could begin its journey south. Engineers designed a pumping station complex at Eshed Kinra capable of moving up to 72 cubic meters of water per second when operating at full capacity. The pumps themselves, manufactured in Britain and shipped to Israel in pieces, stood several meters tall and required specialized installation procedures. Each pump had to operate continuously with minimal downtime, since any interruption would affect water supply across the country. The motors driving the pumps consumed enormous amounts of electricity, making the national water carrier one of the largest single energy consumers in Israel. Engineers calculated that the annual power requirement for pumping alone would exceed 500 million kilowatt hours. To manage these costs and maintain reliability, the system was designed with redundant pumps and the flexibility to adjust flow rates based on seasonal demand. Parallel to the pumping stations, the system required precise filtration and treatment facilities. Water drawn from the Sea of Galilee contained natural minerals, microorganisms, and seasonal variations in quality that had to be addressed before long-distance transport. Treatment facilities built at the source included screening systems to remove debris, sedimentation tanks to allow particles to settle, and chemical treatment systems to prevent bacterial growth during the journey south. The challenge wasn't just moving water. It was moving water that would remain safe and usable after traveling through pipes for days. While construction advanced through the early 1960s, regional political tensions added urgency to the project. Neighboring countries, particularly Syria and Jordan, opposed the water diversion from the Jordan River system, which fed the Sea of Galilee. In 1964, Arab League summit meetings discussed plans to divert Jordan River tributaries before they reached Israeli territory, potentially reducing water availability by up to 35%. These geopolitical pressures transformed the national water carrier from a development project into a strategic necessity. Delays could mean losing access to water resources entirely. Construction crews worked in multiple shifts, often around the clock, to maintain aggressive timelines. In some sections, workers faced difficult conditions. Summer temperatures in the Negev regularly exceeded 40 degrees Celsius, forcing work schedules to shift toward early morning and evening hours. In northern mountainous regions, winter rains created muddy conditions that slowed excavation and made precise alignment of pipe sections difficult. Despite these obstacles, the project maintained forward momentum. By 1963, most major sections were complete and undergoing pressure testing. The system's first operational test came in June 1964, when water from the Sea of Galilee began flowing through the completed sections. Engineers monitored pressure levels, flow rates, and water quality at dozens of checkpoints along the route. The initial flow was set at a conservative rate, while technicians verified that joints, welds, and pump operations performed as designed. Over the following months, operators gradually increased flow to full capacity, and the national water carrier officially entered regular service. The impact of the national water carrier became visible almost immediately in the Negev region. Agricultural settlements that had struggled with limited well water suddenly had access to consistent supply. Kibbutzim and moshavim in the northern Negev expanded their cultivated areas dramatically. Farmers began growing water-intensive crops that had been impossible in the desert climate: tomatoes, peppers, cotton, and citrus fruits. By the late 1960s, agricultural output in the Negev had increased by over 400% compared to pre-carrier levels. Urban development followed the water. Beersheba, the largest city in the south, grew from a population of about 80,000 in 1964 to over 140,000 by 1975. New residential neighborhoods, industrial zones, and infrastructure projects became feasible with reliable water supply. Smaller towns throughout the region experienced similar growth. The demographic shift that Israeli planners had sought, moving population and economic activity southward, began materializing as the water carrier proved its capacity to sustain life and industry in previously inhospitable areas. The engineering success, however, came with significant challenges. Operating costs proved higher than initial estimates, particularly energy expenses for pumping. The system required constant maintenance, as pipes, valves, and pumps experienced wear from continuous operation. Water losses through evaporation in open canal sections and minor leaks in underground pipes totaled approximately 10% of transported volume annually. Engineers worked continuously to reduce these losses through system improvements and more efficient components. As Israel's population continued growing through the 1970s and 1980s, the national water carrier underwent multiple expansions and modifications. Additional pumping capacity was installed at key points to increase maximum flow rates. New branches extended the network to previously unreached regions. The system integrated with local water sources, including wells and smaller reservoirs, creating a unified national water grid rather than just a single north-to-south pipeline. One major adaptation came with the development of advanced water treatment technologies. As understanding of water quality improved, additional treatment stages were added to remove specific contaminants and manage seasonal variations in source water composition. Desalination plants, built along the Mediterranean coast starting in the early 2000s, eventually connected to the carrier system, supplementing natural sources with treated seawater and reducing dependence on the Sea of Galilee. The system also incorporated sophisticated monitoring technology. By the 1990s, computerized control systems tracked flow rates, pressure levels, and water quality in real time across hundreds of monitoring points. Operators in central control rooms could adjust pump speeds, open or close valves, and reroute water through alternative paths to respond to maintenance needs or emergency situations. This level of automation transformed the carrier from a passive infrastructure into an actively managed network. Today, the national water carrier remains a critical component of Israel's water infrastructure, though its role has evolved significantly from its original design. The system now works in conjunction with 5 major desalination plants that together produce over 600 million cubic meters of fresh water annually. Rather than drawing heavily from the Sea of Galilee, the carrier increasingly moves desalinated water inland and even reverses flow direction during certain periods, replenishing the lake with treated seawater to restore depleted levels. Climate change has added new pressures. The Jordan River Basin has experienced reduced rainfall over the past 2 decades, with some years seeing precipitation levels 20 to 30% below historical averages. The Sea of Galilee's water level fluctuates more dramatically than in previous decades, sometimes dropping to levels that approach the ecological red line. These changes have forced operators to manage the system with greater flexibility and rely more heavily on alternative sources. The infrastructure itself requires continuous investment to remain operational. Sections of the original 1960s construction have been replaced or upgraded as materials aged and technical standards evolved. Pumps that once represented cutting-edge technology have been swapped out for more efficient modern equivalents. Some open canal sections have been enclosed to reduce evaporation and prevent contamination. The cost of maintaining and improving the system reportedly exceeds $200 million annually, but the alternative, losing the capacity to move water across the country, would be far more expensive. The National Water Carrier stands as one of the most consequential engineering projects of the 20th century, not just for its technical achievement, but for demonstrating that large-scale environmental manipulation could succeed when backed by careful planning and sustained commitment. It turned theoretical concepts about desert development into reality, proving that water scarcity wasn't an absolute barrier to settlement and agriculture. The system moved over 70 billion cubic meters of water in its first 50 years of operation, enabling population growth, economic development, and agricultural expansion that would have been impossible otherwise. What lessons does Israel's artificial desert river offer for other water-scarce regions facing similar challenges? Let us know your thoughts and subscribe for more stories from Worldwide Arch.